Alright, here we go. iChem lesson 13, our first one in unit 4, on writing and balancing chemical equations. We practiced this a little bit in class today with the simulation, and now I just want to lay down some ground rules and steps for you. First, though, some definitions. So chemical reactions are defined by process by which the atoms of one or more substances are rearranged to form different substances. This word here, rearranged, is really important. It means that nothing is going away. No new atoms are created or destroyed. They're purely rearranging, which satisfies the law of conservation of matter. You should have Googled this in class today and found that matter is not created or destroyed during a chemical reaction. So let's go through the steps of writing a chemical equation. So you'll read a description of the reaction in words. There'll be the names of the compounds and a description of how they're reacting together. Note what is being reacted with what. These are called the reactants. They show up on the left side of the equation before the arrow. Note what is yielded, produced, or formed. Those are all possible words. Those are called the products, and those show up on the right side of the arrow in the reaction equation. You'll need to write the formulas for each compound, so take the name and write the formula following all of the rules that we learned in the last unit, deciding if it's an acid, ionic, or covalent, and following the set of rules that go with that type of compound. We're going to use the plus sign to represent and in the reaction when we have more than one reactant or product. And we're going to use the arrow to represent the produces or yields going from reactants to products. And where available and where necessary, we'll include states of matter. So whether it's a solid, liquid, gas, or something called aqueous, and we'll do a little bit with aqueous this week. What it really means is just dissolved in water. So let's do our first example. We have sodium permanganate reacts with magnesium chloride to produce sodium chloride and magnesium permanganate. Now remember, first step to read the description of the reaction is what I just did. Now note what's being reacted with what. The sodium permanganate reacts with magnesium chloride. These are our reactants. And then sodium chloride and magnesium permanganate are produced to produce sodium chloride and magnesium permanganate. So now I need to write the formulas for each of these compounds. Sodium permanganate. Sodium is a metal, so this is an ionic compound. I need to start with my ions. Na plus, and permanganate is MnO4 minus. When I swap and drop here, I get Na MnO4. That's sodium permanganate. Reacts with, so I'm going to put a plus sign to indicate there's another reactant. And then I have magnesium chloride. Another ionic compound, because magnesium is a metal. I have Mg2 plus and chloride, ClO2 minus. When I swap and drop here, I get Mg, and then in parentheses, ClO2, and then a 2. Ideally, you would write all of this on one line. You can see that I'm running out of space here, so I'm going to draw the arrow to show produced, and then what should be up here on the line, I'm just going to write underneath. So now I have sodium chloride. All of these are ionic compounds, right, because sodium and magnesium are in all of them, they're all metals. So I can just recombine. Now I have these two ions, sodium and chloride. When I swap and drop those, I get NaClO2 and magnesium permanganate, Mg2+ and MnO4. Swap and drop, Mg and then MnO4 in parentheses with the 2 underneath. Now, no information about states of matter were given to me. Nothing said solid, liquid, gas. Technically, for this reaction to happen, all of these need to be dissolved in water, so we would want to include the AQ, but we're going to worry more about that in the next couple of days. Let's do another example. So here we read the description of the reaction. Solid iron reacts with oxygen gas to produce solid iron 3 oxide. If I underline my reactants, I have solid iron, oxygen gas to produce solid iron 3 oxide. Now, what's reacted? Solid iron and oxygen gas. What's produced? Solid iron 3 oxide. My reactant and my product. Now I want to write the formulas for each compound. Solid iron is just plain old iron. In this case, I am given state of matter, so I'm going to put a little s in parentheses down here to indicate that it's a solid. Now I have oxygen gas. Remember, oxygen is diatomic, so if I'm talking about oxygen not as part of a compound with something else, it's O2, and then we said it's a gas, so the little g. Yields or produces solid iron 3 oxide. Iron 3 oxide is an ionic compound. Fe, then the 3 tells me the charge, O2 minus. When I swap and drop, I get Fe2O3. And then, again, it tells us it's solid, so I can include the little s to indicate that it's solid. The next step in in a reaction is to balance the reaction. Balancing the reactions is what we spent most of our time in class today with. The first thing is you have a skeleton equation. This is an unbalanced reaction. When you're writing the equation, it's really, really important that the formulas are written correctly, because everything from this point forward relies on that. You need to inventory your reactants, inventory your products, insert the coefficients, and if necessary, reduce the coefficient. So here's my skeleton equation. It's the same equation we wrote on the other side of our notes, but I left some space in it to include coefficients. Okay, so I have my skeleton equation. I need to inventory my reactants and products. So I have sodium. In this type of reaction, you'll see that permanganate and chlorite, they're polyatomic ions. They stay together. So I can actually inventory just the ion. I don't need to count them up separately. I can inventory permanganate, magnesium, and chlorite. Now create a table with reactant side and product side. Notice, now let's count them up. On the reactant side, I have 1 sodium. On the product side, I also have 1 sodium. Permanganate, on the reactant side, I have 1 permanganate. On the product side, notice here permanganate's in parentheses with a 2 outside of it, so I have 2 permanganate. Now magnesium, reactant side, I have 1 magnesium. Product side again, 1 magnesium. Last one, chlorite. Chlorite over here appears in parentheses with a 2 outside, So I have a two of them, and on this side I have no parentheses, so I have 1 chloride. Now I notice I have some points where it's not balanced. Permanganate is unbalanced and chlorite is unbalanced at this point. So for now, sodium is balanced. I'm going to leave it alone and move to permanganate. I notice that I have 2 permanganates over here and only 1 over here. To balance it, I add coefficients. To make the permanganates balance, I need 2 sodium permanganates. When I do that, that gives me 2 permanganates, but also 2 sodiums. The 2 also is in front of the sodium. So now my permanganates are balanced, but my sodiums and my chlorides are still not. I have 2 of each of them on the reactant side, the left side, and 1 of each on the right side. If I put a 2 here in front of sodium chloride, now on the reactant side I have 2 sodiums and 2 chlorides. You'll notice now I am balanced. 2, 2, 2, 2, 1, 1, 2, 2. This is my balanced equation with these 2 coefficients here. Alright, here's our last example. We have a skeleton equation. I'm going to inventory my reactants and products. I have iron and I have oxygen. Now notice I'm not in the previous one, I can't just count up my polyatomic ions. They don't exist here. I just have 2 different elements. I'm going to total them both up. Reactant and product side. On the reactant side I have 1 iron and 2 oxygens. On the product side I have 2 irons and 3 oxygens. Now here I notice that my irons don't match and my oxygens don't match. It's actually a good practice in these kind of equations, and you'll kind of learn the little tricks along the way, and I'll help you with some hints. If you have only 1 metal, save that metal for last and try to balance the other things first. So here I have my oxygens out of balance. There's nothing really I can do to get 3 on the left, and there's nothing I can do to make 2 on the right. So what I need to do actually is look for the lowest common factor of these, which would be 6. So I want to try to get 6 oxygens on each side. I would accomplish that by, if I put a 3 here, that would be 6 oxygens. Each oxygen molecule has 2, and there are 3. 6 times 2 is 3. 3 times 2 is 6. Now over here, I would want to do the same thing. I have 3 oxygens. 2 times 3 is 6. Now count my irons. I have 4 irons. So now I need 4 irons over here. I put in that 4. And I'm done. So we'll spend a lot more time in class practicing balancing equations. This is another one of those things that requires just lots of practice. Hopefully you notice that by now, to be able to accomplish this though, you need to be pretty proficient at writing formulas. If you are still struggling with formulas, you need to come in for help. We're going to focus from this point forward on practicing balance and the newer stuff. Formulas should be something that you know how to do. So don't forget to do the Google form. You should have everything you need to get 100% in your notes now.